What's up, scholars? Today we're talking about solving exponentials. Look how clever that title is. Yeah, why would we ever need to solve exponentials? You know, it's a good question. Let's remind ourselves what an exponential is. Something like y equals 2 to the x. That is something that has a y-intercept at 0, 1. Because if we plug 0 in here, anything to the 0 power is 1. And then it grows slowly at first, and then faster and 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 faster. Cool, so usually this y value, gesundheit, is some total, and that x is often time. So we're searching for at what time do we get some total of a thing that grows exponentially. So that's what we're going to be using this for in a context. All right, cool. Let's get to it. Before we get into that, we need to learn a new tool called changing of base. So for example, if we have something that is log base b of c. Wait a second, why are you talking about logs? We're talking about exponentials. They're related, right? They are inverse functions. They show up together all the time. So that's why. If you have something that is log base b of c, you can change this base to any number that you want by rewriting this log base b of c to pick your new base, log base a of c divided by log base a of b. Why would you do that? Well, sometimes you don't know what log base b of c is, but if it was a different base, like 10 or 2 or something, then you could evaluate it. Let's do some examples so I can show you what I'm talking about. Our first example says, evaluate log base 4 of 8. So let's just think about this for a second. This equaled some value that would be 4 to the x equals 8. 4 to the x equals 8. I don't know the answer to that. 4 to what power equals 8? Well, definitely not 1, because that's 4, and definitely not 2, 16. I'm not trying to guess something in the middle. Maybe it is 1.5. I don't know. Instead, if I could make this if we could use base 2, I know what 8 is in base 2. It's 2 to the third, and I know what 4 is in base 2. It's 2 squared. So those could be evaluated. So let's change this log base 4 of 8 into some base that is useful, which is 2. So this becomes log base 2 of 8 over log base 2 of 4. And again, we know, let's just convert to exponential really quick. 2 to the y equals 8. 2 to the y equals 8. That means this y would equal 3, meaning that log base 2 of 8 equals 3. And same thing here. We'll call it z now. 2 to the z equals 4. 2 to the z equals 4. That means z is 2. That means log base 2 of 4 is 2. And I guess I was right. This log base 4 of 8 is equal to 3/2. So really, 4 to the 3/2 is 8. Nice. Anyway, this is a little easier. This involves some guessing. There's no need for guessing when we can find actual answers with the maths. Let's do another one of these examples. Solidify this change of base in your noodle. For this one, let's do log base 32 of 8 Do I know what that is right now? 32 to the x equals 8. 32 to the x power equals 8. Yeah, I don't know. Some sort of fraction situation again. So let's convert to a base that is helpful here, which is going to be what? Well, 2 to the third is 8, and 2 to the fifth is 32, so I want a base of 2. So we'll do log base 2 of 8 over log base 2 of 32. Again, how did I pick base 2? Well, I know how to express the numbers 8 and 32 as 2 to some power. So that's how you're going to pick it. It's most likely going to be 2 or 10 or maybe 3. I mean, we know our cubes reasonably well. 3 cubed is 27. 3 to the fourth is 81. Like, pretty low numbers. Or 10. 10 is another popular one. Okay, anyway. 2 to the what power is 8. We solved that already. That was 3. And 2 to the what power is 32. Well, that's 5. 2 to the fifth power is 32. So our answer here is 3/2, and we found that by changing the base to a base that's useful and evaluating the top and the bottom. Nice. Alright, so now let's talk about using logs to solve exponentials. Because after all, that's what we're supposed to be doing in this video, right? Solving the exponentials. So let's say, for example, we have 3 to the x equals 4. I don't know about you, but I don't know how to express 4 as 3 to some power, and then we can set the exponents equal to each other, so that's not going to work here. What we can do is take the log of both sides. Log is an operation, so we can do that to both sides and maintain equality. Just like we can multiply on both sides, divide, add, subtract. We don't mess up that thing being equal, these sides being equal. So we can take the log of both sides. And we're going to take the log base 10 of both sides because that's what your calculator will default to. So we'll take the log base 10 of 3 to the x, which will be equal to the log base 10 of 4. And then we remember that we can bring this exponent out in front. We also remember if it is base 10, we don't have to write that 10. That is our standard base, assumed base. So x times log of 3 equals log of 4. Again, we're trying to solve for x, so we can divide by log 3 on both sides. We'll get x equals whatever answer we get when we plug log 4 divided by log 3 into our calculators, which I'm going to have to go and do on the internet real quick. Yeah, I only have my little 4-function calculator with me right now, so I had to Google log calculator and plugged it in, and we get 1.26 for our answer. So again, what did we do? We had an expression that was 3 to the x power equals 4. We couldn't solve that easily. So we took the log base 10 of both sides. That exponent popped back out in front. We divided by this log on both sides to get the x by itself. And used a calculator for that goodness. Cool. Let's do that one more time. Okay, for this next one, we have 3 times 4 to the x minus 2. Minus 2 equals 22. Alright, so we need to get this expression by itself first. So let's add 2 on both sides. So we've got 3 times 4 to the x minus 2 equals 24. Then we'll divide by 3 on both sides. And get 4 to the x minus 2 equals 8. Cool. Cool beans. Well, we could take the log of both sides here, but now that I'm looking at it, we could also express both the 4 and the 8 in terms of 2 to some power, which sounds nicer because then I don't have to use a calculator. So let's do that. So 4 is actually 2 to the second power, all of that to the x minus 2. And 8 is 2 to the third power. Now we know that when we have exponent to an exponent, we multiply. So this is 2 to the 2x minus 4 equals 2 to the third power. These bases are the same, which means these exponents must be equal to each other. So we set 2x minus 4 equals 3, 2x minus 4 equals 3, and solve for x. So we get 2x equals 3 plus 4, which is 7, divide by 2. So x equals 3.5. Oh yeah, oh yeah. Do you know there's a place on the internet where we could have plugged this in and it would solve it for us and maybe even show us the steps? Yeah, I'm going to share with you a secret that everyone should know, should be public knowledge, called the Wolfman. Alright, here it is, called Wolfram Alpha. I would highly recommend saving this webpage for future use. So I just typed in our question, 3 times 4 to the x minus 2 equals 2, and then double check that the input is actually the question that I want. Otherwise, I probably need to add some like parentheses somewhere or something. Anyway, it's all good. They give us a nice plot of what that function would look like. An exponential, right? It grows slowly in the beginning and then faster and faster and faster and faster and faster. And then they set this equal to, obviously, because it's set equal to the number 22. And then we find the point of intersection where these two things equal each other, that place on the graph, and the number 22. Some alternate form, not sure how that's helpful. That one I could see being useful. And then the real solution, 7 over 2, 3/2. That was the same thing that we got. So, if you ever get real stuck, ask the Wolfman. Help you out. All kinds of beautiful things. Alright, let's do the dang thing. Let's solve an exponential, and we'll check our answer. Good skill to have as well. Alright, we have 3 to the x minus 4 equals 66. I don't know 66 as any base to any exponent. 64, yeah, no, I got you, but 66, not today. So we're going to have to use our log trick where we take the log of both sides. Log of 3 to the x minus 4. Again, what base is this? 10, son! That's base 10. Log base 10 of 66. Why is it 10? Because that's what I assume if I don't write anything. That's what you'll calculate. It assumes if you don't write anything, we use base 10. Got it, got it. Alright, cool. The exponent goes out in front. So we have x minus 4 log of 3 equals log of 66. Now we're just logging on both sides. We have x minus 4 equals log 66 of log 3. Add 4 to both sides. I'm just, I don't know what any of these numbers are. I'm just doing the operations here, and then I'm going to plug it in and see what we get. So we have x equals log of 66 over log of 3 plus 4. And now I definitely need some computational assistance. To the internet! So there we go. We plugged it into our Googles and get x equals 7 point, let's just round the nearest 10th, call it 7.8. And then we'll go over to the Wolfman and check it out. So I plugged in our question, 3 to the x minus 4 equals 66. Got an input. That's what 3 to the x minus 4 looks like. And that's where it intersects the number 66. Here's an extra credit opportunity for you. There's an alternate form of this equation. 3 to the x minus 4 equals 66. Is equivalent to 3 to the x equals 5346. If you can explain why, just write out how to get from 3 to the x minus 4 equals 66 to 3 to the x equals 5346. I will give you 5 whole bonus points. That's an entire assignment's worth. So if you're feeling saucy, go get you some extra credit. Anyway, here's our real solution. They didn't give us any numbers. This is the exact answer. As soon as you take a log, you have to, and you want to express it as a decimal, you have to make an approximation. You have to round it somewhere. Like we rounded to the nearest tenth and said 7.8. But that is no longer an exact answer. That's an approximate answer because we chopped off a bunch of decimals there, which are really part of the answer. So as soon as you take the log, you got to give an approximate form, which is what we're looking for. We want a decimal here. And drum roll, please. 7.8. Well, hey, nicely done. Great work, everybody. All right, let's tell a story, shall we? In 2014, the population of Indianapolis was 838,000, growing at 1.1% per year. When will the population, according to this information, be 1 million people? I mean, I don't know. I'm going to need some equation here. Yeah. It says we have a starting value. We are growing. This must be exponential growth. We want to know when this is happening, so we're searching for a time. What was our equation for exponential growth? The population at time t equaled the initial population times 1 plus the rate to the time. Okay, we're getting somewhere. So we're going to find the population at some time t is equal to the initial population. That's our 838,000 times our 1 plus our rate at 1.1. 1.1% is really 0.011. Okay, so 1 plus 0.011 is 1.011 to the t. There's our equation. All right, now we can work with this. Okay, rewrote that equation so it wasn't quite so smashed. So our population at some time, t, is our starting value times our 1 plus our rate, so 1.011 to that time t. Now we want to know when is the population 1 million. So we're going to be solving for the when, which is t. We want the population to be 1 million. 1,000,000 equals 838,000 to the 1.011 to the t. Sweet. Let's do some division and get that expression by itself. Calculator, 1, 2, 3, 4, 5, 6, divided by 838,000 equals 1.193. That should be enough to the 1.011 t. How is that? It's just computation. You just gotta plow through it. Okay. Well, I don't know what that is. As a power to a something? No way. Let's use our log trick. Let's take the log base 10 of both sides. Log 1.193 equals log 1.011 to the t. The t comes out in front. So we've got t equals bloop bloop blah blah. Bleepity bloop bloop bloop. Divide by log of 1.11. Log 1.011. Boom boom. Go ask the internet for some help. Alright, the internet says our t equals 16.1. What were we solving for? The time it took for Indianapolis's population to be 1 million. Our original date, let me say, well, let's bring it back here. We got t equals 16.1. We started counting in 2014. So plus 16 years. What are we saying? Is that 2030? In the year 2030, we should have 1 million people in Indianapolis. How many people do we have right now? Well, let's go ask the internet. So the internet says in 2018 we were at 876,000, but that's not what we want. This says 869,000 in 2019 by U.S. population. I don't know what that website is. It says the current population is over 1 million. Again, I don't know what that website is. I'd have to check out its validity, but why would that possibly make sense? Based off the information they are saying here, at least. Because this says it increased 1.46% from 2019, and in our model, we said it was only increasing by 1.1% every year. So we could be, changing our rates of growth. Anyway, we're going to cut it off there. Remember, there's an extra credit opportunity back earlier on in the video. Just send me how you worked it out and prove that those things were equivalent. And scholars, we're almost done. Did you realize that? We're so close to the end. Keep on hustling. I love you so much. I'll see you next time.